We are going to be starting section 3.2, which is graphs of equations. I want to know what you guys remember about graphing. So we're going to start with the basics. That first equation up there, y equals mx plus b, does that look familiar?
Yeah.
Yes. Does anybody remember what we call that?
Best fit. No, wait.
Close. Slope-intercept form. When we have a line of best fit, it is usually written in this form. So we have slope-intercept form for our line. Why do we call it slope-intercept form?
Because we got a y-intercept and slope.
It tells us our y-intercept and our slope just at a glance, right? Which piece in that equation is the y-intercept part?
B.
B. And which piece is the slope? M. That's okay. You're really close. It's the m that's the slope. The x is our variable. So that tells us that it's our independent variable there. M is the slope. B is the y-intercept. X and y are points that are on the line, as long as it makes the equation true. And so if I were to write an equation in slope-intercept form, so something like y equals negative 3x plus 2. How would I graph that?
Start on the 2 on the y.
2 on the y-axis, so 0, 2. And then go where?
We do negative 3 over 1, so rise over 1. So it'd be negative 3 to the left, and then up 1. Or
Remember, you said negative 3 over 1, and it's rise over run, right?
I meant down 3 and over 1.
Down 3. When you say over, which way do you mean? Because
Right.
you told me always to the right. Yes. So down 3, right 1. So from my starting point, I'm going to go down 3 and right 1, down 3 and right 1, down 3 and right 1, until I run out of space, at least on my graph. You guys have a whole piece of graph paper, so don't take it to the edge of your piece of graph paper. You'll run out of room. And I can back this up also, can't I? What would I do to finish it out in the other direction?
Just do the opposite.
Yes, we're going to do the opposite, up 3 and left 1. So right here, and that takes me pretty much to the edge of what I can do. Is it okay to leave a graph like this for me?
No.
No. Did everybody play Connect the Dots as a kid?
Mm-hmm.
Hopefully. Connect the dots where you like ABC order or 1, 2, 3 order. Connect your dots on your graphs. I would think that goes without saying, but every year I'm a little bit surprised that I have to talk about connecting our dots. And I'm going to pop some arrows on the end of this. Why?
Because it keeps going on for.
Yes, it's continuous. It keeps going on forever. Does anybody recognize the form of a line that is right below that? Does that look familiar at all?
Maybe.
A little bit familiar? I really wish they taught this more here at Pike. This is not one of the forms that they focus on a lot here. You guys don't lose much. I'll be able to catch you up real quick. But it's nice to be familiar with this. This is called point slope form. With point slope form, I don't necessarily have the y-intercept, but I have a point that's on the line and the slope. A lot of times what they'll teach you how to do in Algebra 1 is how to take it from point slope form, and then they'll have you distribute and combine like terms so that you can get it in slope-intercept form, which is a great skill to have, but sometimes your y-intercept isn't something pretty. It's like 17 over 3. That's a really hard point to graph. But there's some other point on that line where it crosses nicely and you can get it. That's when point slope form is super helpful. So the point that is on your line would be x1, y1. and then your slope is still m. So let me give you an example of a line that would be written in point slope form, and we're going to talk about how to find that point so that you make sure you can identify it properly. So point slope form, if I had something like y minus 3 equals 2, and then x minus 2. That is written in point slope form. You don't always see the parentheses around the y's on the y side. Sometimes they'll be there, sometimes they won't. Same exact meaning. Notice in the form, what's between these y's here? Negatives. What about here? Negative. But when I wrote down what the point was, is it negative? No. So just like when we're finding solutions from roots, or sorry, solutions from factors when we're doing quadratics, and you take it and set it equal to 0 and the sign always flips, same exact thing here. So I'm going to write down this equation up at the top of this graph. Can you guys help me figure out the point that would be on this line? What point would we be identifying?
-3, -2.
Close.
Or, I mean, -2, -3. I mean, wait.
X part first.
2, 3.
2, 3. X part of the ordered pair first, so I look in the parentheses with the x, and it's going to be the opposite of what I see, because I would have to take those parentheses and set them equal to 0 to find the x value. That's why your sign is switching. Same thing on the y side. So I know the point 2, 3 is on my line. What's the slope for this one? 2. So I want to graph this. I'm going to go plot the point 2, 3, right here. And then how would I use this slope?
2 up, 1 right.
2 up, 1 right. And straight on till morning. Make sure you can back it up as well. If you wanted to, you can distribute, collect your like terms, put it in slope-intercept form, but that's going to be a lot more work. It's a lot easier if you can just look at that equation, you're like, oh, there's a point, here's my slope, and then you can go right to the graph without having to put it in slope-intercept form first. All right, let me connect my dots. And then we're going to talk about transformations of different types of graphs. Do you guys remember AH and K at all? Does that sound familiar? Good. A, H, and K help me transform any parent function graph. A is going to stretch or compress things vertically, or it will reflect it over the x-axis. How would I know if it's a reflection?
Negative.
Negative. If A is negative. How would I know if it's a stretch?
Less than 1, or maybe it's more than.
Think about when you multiply things. If you multiply by something less than 1, will it make it bigger or smaller? If you multiply by something smaller than 1,
You make it small.
it'll make it smaller. If you multiply by something bigger than 1, it'll make it bigger. Same thing here with a stretch and a compression. So stretch is going to be if the distance from 0, so the absolute value of A, is more than 1. We can have negative numbers that stretch it as well. Negative numbers will stretch it if they're farther away from 0 than 1. A compression has to be closer to 0. So in order for a compression to happen, my A value has to be in between +1 and -1. Yes?
Isn't stretch like more narrow and compress and wider?
That's one way to think about it. Depending on the kind of function we're looking at, it might not be obvious as far as narrow and wider, but like with parabolas, yes, that's absolutely an accurate way to think about it.
So, if it's narrow, if stretch is narrow, why would we multiply by a number that's larger if we want to make it more narrow? Because you were saying like to multiply by a number less than 1, that would make it get smaller.
Mm-hmm. So I want you to remember that we're talking about vertical stretches and compressions here. So when we're talking about something getting more narrow, it gets smaller side to side, but that's the horizontal direction, right?
Yeah.
So what happens to make it more narrow is that each point for the y part gets pulled up higher. So the y values are going to get bigger, and that'll make it narrower. When the y values get smaller, that's going to make it compressed. So that's what's going on there.
Okay.
Yep. All right, so stretches, numbers bigger than 1 or farther away from 0 than 1. I don't want you to get confused and to think that if it's a negative number, that automatically means a compression. It absolutely does not. Positive and negative only affect whether it's a reflection. Once I know whether it's reflected or not, I don't care about the sign of the a value anymore. I'm looking at its absolute value, its distance from 0. Shifting up or down, depending on the textbook that you're reading, sometimes they call it C, sometimes they call it K. In AHK form, you guys are used to seeing this called K. I don't care which way you refer to it. It's always going to be at the very end of a transformation, and it's going to be a plus or a minus on the end. In order to shift it up, this value is going to be added onto the end. And in order to shift it down, this value would be subtracted at the end. And then this wasn't on this slide, but I'm going to add it on here. Your h value will shift things left or right. And we're not going to deal with h today, but I did want to bring it up and talk about it now. It'll shift it left if it's negative, and it'll shift it right if it's positive. Sorry, I know I'm way down at the bottom of the screen there. So positive k value, or c, on the end. If it's positive, it goes up. If it's negative, it goes down. Your h value, if there is one to look at, would always be inside parentheses with x, and that'll do left and right shifting. Because it's inside parentheses, to find the true value, you'd have to set it equal to 0, so it would behave just like this point slope form up here for your h. Anytime it's in parentheses or anytime it's having an operation with the x value, you have to set it equal to 0. You guys ready to do some practice with graphing? All right. Grab a picture of this if you need it. All right. Some parent functions. In order to graph with transformations, we need to have a good idea of the most basic of the different types of functions that we would be looking at. So for quadratics, A and C would be the transformations on there, but the parent itself, the most basic quadratic function, is y equals x squared. Hopefully, as we move forward with graphing, you guys become more and more comfortable with the parent functions, and you don't need to make a table each time. I'm going to put down the table here for notes purposes, but you do not have to make a table to graph these for me. All right, so parent function, y equals x squared. When we go to graph functions, any kind, we get to choose our input values, the independent variable. Which one is the independent variable, the x or the y? X is our independent variable. So we get to pick the x's. I want to know, when I'm graphing things, the behavior that's happening to the output. I want to know what's happening when the x's are positive, but I also want to know what's happening when the x's are negative. It's also really important that I find out what's happening right at 0, because a lot of functions have very peculiar behaviors right at 0. So I want to make sure to include that one as well. So like I said, I'm going to make a table for this. I do not expect you guys to make a table. If you can do this without a table, that's great. As you become more comfortable with it, if you feel like you can let go of the table, that's all right. Yes, sir.
So is y equals 8x squared plus c also a parent function?
Y equals ax squared plus c would be transformations of it. And it's written up at the top there because here in just a minute, we're going to look at some transformations of the parent. So like I said, I want to know what's happening right at 0. So if I choose 0 as an input value for x, I would take it and put it into my function in the place of x. And what are we doing to our x's in quadratics? Squaring them. What's 0 squared? 0. So that means I would have a point right at the origin. I said I want to know what happens when the x's are positive and when the x's are negative. But I want to pick numbers that are easy for me to work with in my head because remember, it's a no calculator course here. So I want to pick numbers that are easy to work with. What happens if x is negative 1?
Then it's y is 1.
Y is positive 1. What about if x is a positive 1? Y is still a positive 1, right? So I get the same output for two different inputs. What about if x is positive or negative 2? 4. Same output, two different inputs. What about if x was positive or negative 3? 9. Same output, two different inputs. There's my basic parent quadratic. Ugh, my hand wiggled a little bit while I was drawing it. Try to make that a little bit better. Parent quadratic. Know it, love it, memorize the pattern, or at least how to recreate that table quickly. For a cubic, my parent for a cubic would be y equals not x squared anymore, but x to the third power, x cubed. Transformations would be a and c. Those would stretch it or compress it, reflect it or shift it up or down. Compare and contrast for me how that's going to be the same and how that's going to be different from the quadratics. Are any of those ordered pairs going to be the same? 0, 0, because if I take 0 and I cube it, I still get 0. Are positive 1 and negative 1 going to have the same output? No. What's negative 1 cubed? Negative 1 cubed is negative 1. What is positive 1 cubed? 1. So I have a point at negative 1, and positive 1, positive 1. That almost looks like a line right there. It's not a line. Because what happens if I use negative 2 as an input?
Yeah, -8.
Negative 8. Positive 2 as an input?
8.
Positive 8. So now it stops looking like a line. It's got this curved shape to it. Right in the middle, where those 3 dots look like they're forming a line, that's actually pretty curved in there. If we were to pick some decimal values and model this with a calculator, we would see a curve happen there. With quadratics, we take the input and square it before we do any other transformations to it. With cubics, we take the input and we cube it before we do any other transformations to it. What about square roots? What are we going to be doing to our input? Not squaring it. Rooting it, yes. We're going to square root it. My parent for this would be y equals the square root of x. I said that I need to know what happens when x is positive. I need to know what happens when x is negative. I need to know what happens right at 0. When I think about using negative values for my input, what problem do I run into here? They'd be imaginary, right? Can I graph imaginary things on an xy axis? No, so I can't have any negative inputs this time. If x is negative, my output is imaginary. So what's the smallest number that I can actually take the square root of if I can't do negatives? 0 is the smallest, right? What is the square root of 0? 0. What point do you notice all three of these parents have in common? 0, 0. They always go through or at least touch the origin. From here, because I get to pick my inputs, and I don't get to use a calculator in here, I want to pick things that I can take the square root of easily. So I'm not going to pick numbers like 2 or 3, because I don't know what the square root of 2 is. Do you know what the square root of 1 is? Square root of 1 is 1. Gavin, you said 4. What's the square root of 4? 2. Do you guys know any others? 9. What's the square root of 9? 3. I could keep going with this, except I'm running out of room on my graph here. So I'm going to connect these dots. Should I put arrows on either end of this? Just on the right side. Why do I put it on the right side but not on the left side? Yeah. If I were to move to the left, there aren't any values back there. They're imaginary. So it has a hard stop at the origin. Why do I have an arrow on the other side? Yeah, I can keep finding more and more numbers that I know the square root of. So if I had a bigger graph, I could keep going. All right, let's look at a couple of examples with transformations now. Now that we have our parent down, we can recreate these tables if we need to. I'm probably going to continue right now to write some tables down so you guys know where I'm getting these points from, but I don't expect to see tables on your work. If you want to, you're welcome to, but I'm not looking for that for points, okay? All right, we got 4 different things here. I'm going to graph these on separate graphs for us. You're welcome to do them all on one or whatever works for you. You know how much paper you've got access to. For this first one, what form is this?
Quadratic.
The very top one, A? That's slope-intercept form. So what shape are we going to be graphing here? A line. This first one is a line. It's in slope-intercept form. Where's my y-intercept? 0, 5. And my slope is 2. So up 2 and to the right 1. I can get 3 points on there before I have to back it up on my graph. Get my line on there. Go. Pop some arrows on the end. It does continue on. What is this second one going to be a graph of? A quadratic. So I'm going to be making a parabola. What's happened to this parabola? Describe the transformation. It's reflected, stretched by 2. So that means the y value is my output. Since there's no left or right shifting here, I don't need to change my x's at all. But that means those y values from the parent, they're all going to be multiplied by -2. So whatever the output was for the parent, I'm going to take and multiply it by -2. So here we go. Will that change the vertex? Will I still have a point at 0, 0? Yes. Still going to have a point at 0, 0, because when I multiply 0 by -2, I still get 0. Positive and -1 on the parent, when I took it and squared it, that had an output of 1, right? -1 squared, +1 squared. Order of operations says I have to do the squaring first, and then I'm going to multiply it by -2. So what would the output be here? -2. 1 times negative 2 on both of those. What about for negative 2 and positive 2? What'd you say?
Negative 8.
Negative 8. Because negative 2 squared is 4 times negative 2 gives me negative 8 for both of these. So it's going to be reflected, pointing down. I feel like my hand's getting shaky up here, but you guys know it makes a U shape. Do the best you can. I'm not grading your art skills. As long as I can see where your points are and you get the basic shape down. Not an art teacher. What kind of function are we going to be doing for part C? What is happening to our x's? Square rooting them. So this is a square root function. When I think about the parent for the square root function, what kinds of numbers was I not allowed to choose? Negatives were off limits. And from there, I wanted to pick inputs that were easy to take the square root of so I could do it in my head. Once I've taken the square root of the input, will I add 1 first or will I multiply by 2 first?
Multiply.
Multiply, because order of operations, you do multiplication before any addition or subtraction. So for this one, I couldn't have any negatives. I could start it with a 0. What will the output be here? 1. What's the next input that I'd want to be using here? Something I can take the square root of easily. 1. I do the square root of 1, I get 1, and then I do what to that 1? Multiply by 2. Plus 1. So what's my output? 3. 1, 3. Something else I can take the square root of easily. 4. When I square root it, I get 2. And then I take that times 2. And then I add 1. 5. Are you guys noticing a pattern in the y's here? What do you think my next output's going to be? 7. What's the input that goes with it? 9. The y's almost look like a linear pattern there, right? Because it's increasing by 2 each time. It's not linear, though, because my x's aren't increasing by the same amount each time. We were picking out x's that we could take the square root of pretty easily. Only an arrow on the right-hand side. I want you guys to do part D on your own. Graph part D on your own. Hopefully, your line is turning out to look a lot like my line. I want to do a couple more graphs of transformations, and then we're going to shut things down so that I can pass back your tests and you guys can see how you did. Okay? So here's the last 4 things that I want to graph. What kind of a shape are we starting with? Part A. What's it going to look like? Quadratic parabola. What's happening to my parabola? Compressed. Close. Up 3. For all the ones today, we're doing up and down. We're not dealing with any left and right. But yeah. All right, so it's compressed. Will that will the compression change my output when the x is 0? No. Will the shift change it? Yes. So when my input is 0, my output is 3. We had also done -1 and -2, +1 and +2. When I take -2 or +2 and I square it, I get 4. And then I want to multiply it by a half. What's half of 4? 2. And then I do 2 plus 3, 5. Anybody want to guess why I skipped the ones for right now?
It's a decimal.
It's a decimal. Doesn't mean I can't do it. Just means I want to give it a minute. When I take -1 or +1 and square it, what's my output? 1. And then I want half of that, 0.5 plus 3. 3.5. It's going to be halfway in between the 3 and the 4 on my graph. So you should notice that that looks wider on the graph than the parent function did. What kind of function do we have going on in part B? Square root function. What's happening to the square root function in part B? Down 4. Other than that, it's exactly the same as the parent. So for part B here, what kind of inputs do I like to use for this?
0, 1, 4, 9.
0, 1, 4, 9. Why do I like those?
Easy square root.
Yep, easy square roots. There's nothing magic about those numbers. I'm just trying to make my own life easier here. So I square root it first, and then I subtract 4. What's my first output?
-4.
-4. So 0, -4. And then we do the next one. I do the square root of 1. And then I I minus 4. And I get an output of -3. Let me misspeak there. What's the next one going to be? -2. And the last one? -1. Notice my y's are moving by 1s. The x's aren't, but the y's are. Only an arrow in that one direction. What form is part C in here?
Point slope.
Point slope form. Point slope form tells me a point on the line and then the slope of that line. What is the point on this line?
2, -4.
Careful, remember you want the x part first and then the y part.
Oh, -4, 2.
-4, 2, because remember we always have to switch our signs since it's inside parentheses. You would set it equal to 0 to identify it correctly. So this is point slope. My point is -4, +2. Be careful when you're doing this on your own. X part of the ordered pair first. I know it's so easy to just track your eyes left to right and grab the numbers. Pay attention. And what's our slope? Slope is 2. So I'm going to plot a point at -4, 2. And then I'm going to use that slope of 2 to get the rest of my points. Means my y-intercept is up there at 10, and my x-intercept is at -5. We've got one more thing to graph here. And it almost looks like what? It almost looks quadratic. Why is it not quadratic?
Because the x and y are replaced.
Yeah.
Switched.
X and y have switched places. When I go to graph things, x is my independent variable, y is my dependent variable. But when I see something like part D, I'm going to pick out the y's because that's the thing that's having an operation happen to it. So I'm going to look down here at part D. And I'm going to kind of do it backwards from what I've done in the past. Instead of choosing my x's, because I was doing things to the x's, I'm going to choose the y's. I still want to pick easy small numbers that I can do operations with, like -2. What happens if I put -2 in here for y? What would I do to it first? Square it. That would give me 4. What's 1/4 of 4? 1. So I have an ordered pair at 1, -2. Is there another y value that would give me the same x value? 2. So that would be right here. What happens if y is 0? 0. Because we're not shifting up or down at all. We're squaring and multiplying. So 0 is going to stay 0. What about positive and -1? 0.25. Positive 1/4. I don't care whether you write it as a fraction or a decimal, whichever way is easier for you to think about it. This is how far to the right I move. So I'm barely moving to the right of the x-axis. And then I go up 1 and down 1. So it's going to be about here and about here. And when I trace this in, it looks like a parabola on its side, a rather wide parabola on its side. This is quadratic-like. All right. So again, I wrote down tables on the notes today so you guys know where I got my points from. You don't have to make tables for me. If you find them helpful, you're more than welcome to do it. I want you to get fast at the graphing, though. So making super detailed tables isn't going to help you get faster at it necessarily. The 3.1 homework is due tonight. 3.2 homework is due on Monday. That means we're going to spend the next 2 class days going over it. I will warn you, especially because we're going into homecoming weekend, this is not a short assignment. Please, please, please do not wait until Monday to start the 3.2 homework. Get some of the graphing out of the way tonight. That's some time-consuming work. As we move forward each day, do a little bit of that homework each day, okay? If you wait until Monday night to get it done, you're not going to get it turned in on time, all right?